Hello friends, welcome to my channel Physics Classes, and today I have brought the second lecture of electric charge and field. In this video we will talk about some attractive force, repulsive force, something about permittivity and the principle of superposition. So let's begin. So before I start the Coulomb's law, like in class 11 you might have learned about the gravitational force. So in that gravitational force we have the two masses, and if there is some distance between them, the force was said to be the attractive force, and it was given as F is equal to G m product of mass by the distance square. So that is for the masses. Now when we replace the mass with charge, so it will show almost like there is some attractive force also and there is some repulsive force also. In gravitation force we have only the attractive force, but here we will have two things. So if you have studied gravitation chapter nicely, then this chapter 1 is almost quite similar to that gravitation force with some difference. So in Coulomb's law, like they have replaced the charge with they have replaced the mass with charge. So what they said is, if I have two charges, 2 point charges, suppose Q1 and Q2. Now this point charges, it may be positive or it may be negative, and the charges is at rest. The charges, both these charges is at rest, they are not moving. So this is Coulomb's law is valid only for the charge at rest. Now when two stationary point charges are there and there is some distance between, then the force is directly proportional to the product of their magnitude. If I write this with the magnitude Q1 and Q2, I can take the mode of Q1 and mode of Q2. Whether this will be negative or positive, I don't care. I will take simply the mode. And it is also said in second line, force is inversely proportional to the square of the distance between them. Now if we combine these two, Q2 by R square. Now if I remove this proportionality sign, the force will be F is equal to some constant K, Q1, Q2 by R square. Or sometimes for to more easy, we write this simply K, Q1, Q2 by R square. We remove this mode. Now what is this K? K is your, if I write K is your Coulomb's constant, or we say sometimes or electrostatic force constant. This value is K is equal to 1 by 4 pi epsilon naught. Now, and its value is 9 into 10 to the power 9 Newton meter square Coulomb minus 2. So this epsilon naught is your permittivity of free space. Now what does this mean? So it means that when you have 2 point charges in a free space, the force is given as this. In other medium, only this will change. If the medium changes, the value of K will also change. So it depends on the medium. But in free space, you will have 9 into 10 power 9, the value of K. One thing in this Coulomb's law is that the last line, the force acts along the line joining. What does it mean? Like if I have 2 point charges, the force, like the resulting force, will act along this line. The force, whether it is attractive or repulsive, it will not act along this line or this line. Okay, so the force will be acts along this line only. If suppose both charges are like charges, then they will repel with equal and opposite force. Both are like charges. Suppose if both and if they are unlike, then they will attract each other. They will attract each other. So that is your about the last line. Now we will see how the Coulomb's law, like force of attraction or repulsion, changes when we change the medium. Now, what is like when we have suppose these two charges Q1 and Q2. Suppose this is your vacuum. Now in vacuum what we have is, in vacuum we have the force K Q1 Q2 by R square, or simply if I replace this it will be 1 by 4 pi epsilon naught. Now epsilon naught here is your permittivity of free space. Now if I take these 2 point charges, in some other medium, let us take that if I have taken this point charges Q1 and Q2 with same distance in other medium. Suppose this is my medium. Medium can be anything, water, alcohol, glass or anything. So if I have taken this medium, so what is the force in this medium? It will be 1 by 4 pi, and this is epsilon Q1 Q2 by R square. Everything remains same, only this permittivity will change. Epsilon here is your permittivity of medium. Now this is the property of a medium which determines how much force they will, attractive or repulsive force they will have in their medium. So more the permittivity, less the force. Less the permittivity, more the force, because it is in denominator. So if the permittivity value is very high, the force will be less. If the permittive value is less, then the force will be high. Now if I divide this F vacuum by F medium, it will be 1 by 4 pi epsilon naught Q1 Q2 by R square, 1 by 4 pi epsilon Q1 Q2 by R square. Everything will, these things will cancel out, and epsilon by epsilon naught will be there. So I can write this as force on vacuum by force on medium is epsilon by epsilon naught, or if I write this as some constant, this is some, it looks like K but it is not that K. So this is called your dielectric constant. This is called your dielectric constant. So I can write this as F vacuum will be your F medium by dielectric constant. This is 1, or I can write this your epsilon is equal to epsilon naught. Means that when we move to the medium, your force becomes less. Now what is your dielectric constant? It is the ratio of permittivity of medium to the permittivity of vacuum. So we can simply say in vacuum the force is very large, and in other medium force is small compared to the vacuum. So, and the value of by solving the problem, if you know the value of epsilon, it's better. So the value of epsilon is 8.85 into 10 to the power minus 12 farad per meter or farad per meter, simply we. Till now we have studied the Coulomb's law in scalar form. Like whenever we have two charges and there is some distance, the force is given as F is equal to K Q1 Q2 by R square. But as you know that your force is your vector quantity. So whenever vector comes, student find a bit difficult while dealing with this vector. So, but when we assume something, it becomes very easy. So here we will assume something like R21 is the position of 2 with respect to 1. Means position of 2. Whenever a person looks from this point to Q2, that is the position of 2 with respect to 1. So R21 means R21, position of 2 whenever a person looks from this to this. And R21 is a unit vector. You might have studied this in class 11. What is your unit vector? So, or in mathematical form, I can write R21 cap is your R21 vector by R21. That is the magnitude of this R21. Now, and what is the force? Force on 2 because of 1. Force on this because of what? Now, if I consider both the charges to be positive charge, let me assume that this is also a positive, this is also a positive. Now, if I have assumed that, then the force on this will be along this side, F21 will be along this side. So, if I write this force in scalar form, it is this. So, if I write in vector form, F21 will be your K Q1 Q2 by R21 square R21 cap. So this is your Coulomb's law in vector form. One more thing, like in books, many times you see that this is your cubes. Now since we know this, we can simply write this. Now F21 is K Q1 Q2 by, if I replace this R21 square, if I replace this with this, it will be R21 cap R21. Or I can simply write this as force is equal to 21 K Q1 Q2 by R21 cube and R21, this is in terms of position vector. So either you write this or you write this. Now this is your F21. You can write in this also F12 also, that is force on 1 due to this, and this R12 is position of 1 as seen from 2. So this is in this direction. So both are in same direction. So your force will be F12 will be, I can write K Q1 Q2 by R12 square R12 cap, or simply K Q1 Q2 by R12 cube R12 cap R12 this. So these things are written in terms of vector quantity. If it is scalar or vector, you just denote first, then you write, then it becomes quite easy. If you write this also, it's okay. If you write this also, it's okay. But while solving the problems, we usually take the scalar form, that is this one. And the force will be attractive when the charges are opposite. If I have opposite charge, unlike charge, then the force is attractive. If I have the same charges or like charges, the force is repulsive. We'll start the principle of superposition. Now the superposition principle is based on the fact that if I have suppose two charges, Q1 and Q2, and suppose there is some distance between them R. The force is given as K Q1 Q2 by R square. Now if I bring the third charge, suppose if I bring the third charge, suppose Q3. Now what will happen to the force between, suppose 1 and 2, force between 1 and 2 is this. Now what will happen to the force between 1 and 2 if I bring the third charge? Whether this third charge will have any effect on this force or not. Or if I bring one more charge, Q4 also, or if I bring Q5 also. So all these charges, will they have any effect on the force between these two charges? The answer is no. So what does it say? The force property of this, the principle of superposition is based. So the presence of two third charge or any other charge will not affect the force between the two charges. So if I have suppose one charge Q1 and suppose this is my charge Q2, this is R12 or R21, this is R, suppose if I write this as R12, if I write this R, this is charge Q3, R13, R14, Q3, Q4, or if I have the suppose Q5, or if I have Q6. Now all this, if I have some attractive force or repulsive force, suppose this is your repulsive minus, then the force will be something like this. This is F12, this is F13, this is F14, this is F15, this is F16, and there will be some resultant force. Let this be the resultant F net. So this F net is given as, according to the principle, superposition principle, F net is the vector sum of all this. 1, 3 plus F14 plus till, if I have suppose n number, then it will be F1 and force on 1 due to all the charges. Or I can simply write 1 by 4 pi epsilon naught. This is Q1, Q2 by R12 square R12 cap plus Q3 R13 square R13 cap and Qn R1n square R1n cap. So in this way we can proceed. Or simply we can write Q1 4 pi epsilon naught. If I replace this with summation sign, this is your I is your J is your 1 to n, I is your 2 to n. So Qi by Rij cap. This is F net. So I can write simply in terms of this. So we'll start the problems here. Now in this equilibrium problems, we will see that if I have two charges, 2 point charges Q1 and Q2, and this is the line bearing of the charges, where should I place the third charge so that the total force on the third charge will be 0. If I have third charge say Q, so that the net force on Q must be 0. Where should I place this Q so that the net force on this Q is 0? Either here or here. So it depends on the nature of the charge. If the two charges are positive, it will be somewhere at different place, and if two charges are unlike, then it will be at different. So first we'll see about if the charges are like charges. Now if I have like charges, first case is your outside. If I have 2 point charges Q1 and Q2, say I have taken this charge to be positive, and the third charge, where should I place? Outside. If the third charge I have placed is somewhere here, Q. So there will be some force on this due to Q1. Let me take this force, this third charge also to be positive. So there will be repulsive force on Q due to Q1. Yeah. There will be another force due to Q2 on Q. That will also be your repulsive force. So F2 will also be positive. So net force on Q must be equal to F1 plus F2. Since both are in the same direction, so net force will be F1 plus F2. Now if I place somewhere here also Q, there will be one force on Q due to Q1, that is in this side, and another force on Q due to Q2, again it will be on this side. So in both the case you have F1 plus F2. So since it is in the same direction, the net force will not be 0. We are adding two things in the same direction, so the net force will not be 0. So what will happen if I take the charges in between? So if I have two charges Q1 and Q2, and the third charge is somewhere here Q, there will be one force on Q due to Q1, that is in this direction, repulsive force on Q due to Q1, force on Q due to Q2 will be this F2. Now in this case we have seen one force is in this direction, other force is in this direction, so there is chance that both force might cancel each other. So F net must be equal to F1. If I take 1 to be positive, I have to take 2 to be F2 to be negative. So there is at least some chance that this force will be 0. Some chances are there that these two will cancel each other. So the net force on this will be 0, and the condition will be F1 must be equal to F2. This is the condition. Now we will see for the unlike charges. If I have minus Q1 and plus Q2, this is of course outside. If I put the charge here Q, there will be one force on this. So since this is negative, this is positive, so the force will be somewhere like this, F1. And there is some force on this, so it will be, the force is like this, F2 will be here. So F net will be how much? If I take F1 to be positive, I have to take F2 to be negative. So there is some chance that net force will be 0. So this side I can put, or if I put this side also, it will be like Q3, due to Q2 it will be this side, due to Q1 it will be this side. So there is some chance that for unlike charges, when we put the charge outside, the force will be 0. And for inside, when we have unlike charge, Q1, Q2 minus plus Q, inside it will be force on Q due to Q1 is F1 is this side, and again this will also be this side. So even in this case, F net will be F1 plus F2. So there is no chance that this force will be 0. So when we have two like charges, we put the charge in between, somewhere in between, and we have unlike charges, we will put either this side or this side. Now it depends on the things, like if I will put the charge close to the charge who has less magnitude, and we will place near to the smaller charge magnitude wise, and here also near to the smaller charge magnitude wise. So finally we compare the electrostatic force with the gravitational force. What are the similarities and dissimilarities between them? The similarities are that both the force obeys inverse square law. What is inverse square law? That is, if force is inversely proportional to the square of the distance between them. It has been seen in both the cases, that is in gravitational force also and in gravitational force also and electrostatic force also. Second case is both the force are central force or radial force. So in both the case we take the distance from the center to center. This distance is taken from center to center. So both the force are central force, or sometimes we say radial force also. Third point is force are conservative. Conservative means the work done by the gravitational force or the electrostatic force is independent of the path it has traveled. All the work done depends on the initial and the final point only. Dissimilarities is very easy only. Gravitational force is attractive only, and while electrostatic is attractive as well as repulsive, depends on the nature of the charge. Second point is force depends on the medium. Electrostatic force depends on the medium. We have seen that force is 1 by 4 pi epsilon naught Q1 Q2 by R square. Your epsilon is the permittivity of the free space, and it depends on the permittivity, medium to medium. While gravitational force is your F is equal to G m1 m2 by R square, where G is your universal gravitational constant. Third point is electrostatic force is stronger than the gravitational force. Now if I write this, your chalk sticks to that. So even the Earth mass is very large, the chalk doesn't fall down. So your electrostatic force is much higher compared to the gravitational force. Now next we have the limitation of Coulomb's law. Now first is it is not applicable to the extended mass. So whenever we have some point charges, this is applicable. But suppose if I have some extended mass like this marker or this duster, it is not applicable. If I have two extended charge like this, so it is not applicable in this case. So it is applicable only for the point charges. And second point is, if the charge is moving, it is not applicable. Your Coulomb's law is not valid when the charge is in motion. It is valid only when the charge is at rest. When the charge is at rest, then only it is applicable. So friends, that's all for today. In our next video, we will discuss about the electric field. So till then, take care. Bye bye.